let's start talking about random processes. Now, power spectral density, okay, is a function that shows the strength of the variations as a function of frequency. Now, we've heard of function of frequency already, okay, because power spectral density is actually the Fourier transform of what's known as a correlation function. We're not going to focus too much on the sums and the maths behind derivation, but that's what it is. It's a Fourier transform. And in random vibration analysis, the acceleration power spectral density, okay, because we're often in vibrations, we're dealing with acceleration, not power in terms of watts, but acceleration in terms of g, okay, has the units of g squared per radian per second, okay, because it's a function of frequency, or you can have it in terms of hertz. Hertz is also a frequency, okay, so depending on which units you use, you've got radians per second or hertz down there. And like I said, the g is to do with acceleration. And that represents how acceleration power, in a sense, power in inverted commas, is distributed over the frequencies. And so you can end up with a function that looks, before I do that, power spectral density is represented by S, okay, and like I said, it's a function of frequency. So in here we've got in omega, if it's in radians per second, or F, if it's in terms of hertz. And I'll talk about how you can convert between the two in a minute. So power spectral density is represented by S of omega, or S of F in hertz, and a certain function could be written like this. It's double-sided, if we've got in terms of omega, okay, and so we've got a peak around this point, which I'll call minus omega naught, and this point, which is plus omega naught. And this is my power spectral density for a certain function, okay. That's an example. It's even, you can reflect about the y-axis, and it's real in this case. Again, I won't go through the derivation, but to convert between a double-sided spectrum in terms of radians per second and a single-sided spectrum in terms of hertz, which you'll need, you multiply the double-sided one by 4 pi to get your frequency. Okay, that's just the relationship. Again, that's on the equation sheet, so you don't need to worry too much about that relationship. But like I said, you can go through the derivation if you want to. I don't think I included that in chapter 9. I might have done, I'm not sure. Let's see. No, I didn't. But you can go through the derivation if you want to. Now, the interesting thing about power spectral density is if you take the integral of the power spectral density, okay, with respect to omega between minus infinity and infinity, you get the mean square value, the expected value of x squared. And this is important because if you take the square root of this term, you get the root mean square, which is an important statistical measurement. And as we discussed earlier, the root mean square is basically the magnitude. I've written the actual definition. Statistical measure of the magnitude of a varying quantity, okay, which is what's useful to know about certain random processes. So that's important. Like I said, if you've got the power spectral density of your output, okay, of your vibration, whatever, you take the integral of that over all frequencies, you get your mean square value. You take the square root of your mean square value, you get your RMS, which is what we're often trying to find, the RMS value. Okay, the integral of your power spectral density with respect to frequency over all frequencies will be your mean square value. Square rooted, you get your RMS. Now I said there was an important word I mentioned in that description just a second ago. I said this is a power spectral density of your output. Okay, output being the important word. Now often processes will have an input and an output. And it's important, what you may have is your power spectral density of your input. For example, if you're looking at a suspension system, that input could be the road surface. So we know the power spectral density of a road surface could be some signal or whatever. Often it's a constant, but there'll be some power spectral density over all frequencies that will be your input. You then have to convert that to the output and then integrate it to get your mean square value. Okay. Now, how do we convert between the two? Well, we use something called the complex frequency response function, which is H. Okay, and that's the transfer function. There should be a word function in there between the input power spectral density and the output power spectral density. Now, how do we get this? Well, basically, let's assume we've got a mass string damper system. My input is a force. My output is my displacement. Okay, which makes sense. And you make these substitutions. Okay, you make the substitution, you stick in, for F, you stick in F naught E j omega t. Notice this is an equation for an oscillation. Okay, and for X, obviously, we also get X E j omega t. And obviously, to get X dot, we differentiate this once with respect to time. I get my j omega coming out, and then X E j omega t. Double dot, I get another j omega out, so I get minus omega squared X E j omega t. And so I put them in my equation, and I rearrange. So I get this is my equation of motion, okay? The E j omega t's will cancel each other out, they're in every term. And then I can rearrange it, putting my output over my input, okay, to get my function. And so output over input, so in that case, X divided by F is my H omega, which is my complex frequency response function, and looks like this. So that's my H omega. As an aside, when you cover control next year, control systems, in semester 2 of this module, you'll come across this process, okay? You'll be using Laplace notation, and then to find the frequency response, you replace every term of every S term, okay, which you can put in here with a j omega, and you end up with the same equation, okay? It's essentially what you'll be doing quite frequently. And you'll be covering transfer functions as well. But this is how we're going to use it here. So you get H omega, and the relationship between the output and the input power spectral densities is given by this equation, where you take H omega, you take the magnitude, square it, multiply it by your input power spectral density, will give you your output power spectral density. And this is a term you integrate to get your expected value, sorry, your mean square value. Okay. So you're often given this equation, you're given this function, whatever that is. It could be a constant. This you can find from your system, so you have to know what the system sort of looks like to get your complex frequency response. You multiply it, like I said, you take the magnitude of that squared, and that will be your output. Okay, you integrate this or this term, and you get your expected value. Now, there's a little trick that we all need to know to integrate that, because it's quite difficult. But we'll sort it out. So like I said, you take this term, magnitude squared, so that's in there, multiplied by your input power spectral density, which will be given between minus infinity and infinity, and you'll get your which is the integral of this, which is your expected value, or expected value of the square, so the mean square. Now there's a useful integral identity that's on your equation sheet, okay, and that integral looks like this. Okay, so if you've got a function that represents this form, okay, take the magnitude squared, you integrate with respect to all omega, okay, then you know that your answer is going to look something like this: pi, and then you've got b naught, which is this term, divided by a naught, which is this term, times by a2, which is this term, plus b1 squared, which is this one, okay, over a1 times by a2. That's an identity. So if we've got, we'll go through an example that we'll use that in a second. And here's an example. The single degree of freedom system is subjected to a force whose spectral density, SF, okay, so of a force, say, plus omega minus omega of S is equal to S naught. So it's a constant term. It's a value, a certain value, S naught. Okay. Find the complex frequency response function of the system, the power spectral density of the response, and the mean square of the response. And so this system looks like this. Okay, it's a mass spring damper system. I've got a force that's being input. I've been given the PSD as the force, and I've got to find my various terms in terms of X. Okay, I've got to find the it says there, I've got to find the complex frequency response, the power spectral density of the response, and the mean square value of the response. So, complex power frequency response, okay, so there's my input, like I said, it's a constant force. There's my equation of motion, okay, that should be straightforward. You should understand that if you've got a mass spring damper system, then you've got that equation of motion. That's pretty basic. And obviously, if you go through the process of replacing x with x, big X, e to the j omega t, and so on, you end up getting this as your frequency, complex frequency response. And plotting that, you get something that looks like this with two natural frequencies in there. Okay. So there's our complex frequency response. That's part A. Part B, we need to find the power spectral density of the output. Well, we know the output, which is x, is going to be the magnitude of the complex frequency response squared times by the frequency response to the input. Okay, so obviously I've got this term here, times by s of 0 gives me my output. Okay, and if I was plotting that, I get something that looks like that. And that makes sense because we've got a constant term multiplied by that frequency response term. So you get something that looks very similar. Okay. Now to find the expected value, there should be an equal sign here for the eagle-eyed among you. Okay. Apologies about that. Make a note of that. Equals. The expected value, so the mean square value of the expected value of the square, or the mean square value, we know is the integral of your output power spectral density. Okay, so you take your input, the input power spectral density multiplied by your frequency response function. Okay, and you get your output. And so obviously S0 is a constant, so that can come outside the integral. We do the integral of this, and like I said, what we use is we use that identity that I've given you, where we had, you know, the B0 plus B1, yeah, and so on, and you can work it out, and you end up getting this as your term. And so, and yeah, like I said, you can do some simplification and stuff. You end up getting pi times S0 divided by Kc is your expected, your mean square value. You take the square root of this, okay, you'll end up getting the RMS. Now, how did I go from this line to this line? Well, like I said, I used that identity. Okay, so there's my identity, and in this case, if you go back to the equation, you can see that on the numerator I've got 1, so that means that up here I've got B1 must therefore be 0, okay, and B0 must therefore be 1. And on the bottom I've got minus m omega squared, so my coefficient for the omega squared is minus m. My coefficient for j omega is c, and my coefficient for the term without any omegas on the end is k. And so I've got, so like I said, omega squared is minus m. Okay, so over here I've got minus a2 omega squared, so that must be m. A2 must be m. My j omega I had c, okay, and my one without anything was k. So a0 must be k, a1 must be c, and a2 must be m. Like I said, b0 is 1, and b1 is 0. You get those terms, and hence you find the solution. We have b0, which is 1, divided by, so 1 squared divided by a0, which was k, so 1 divided by k, times by a2, which is m. So we've got m over k, plus b1 squared, which is 0, and then on the bottom we've got c times by m. And if you do like I said, if you go through the process, so there's my term, 1 over k times by m plus 0 over cm. Obviously what happens is the m's will cancel out, and I get 1 over ck there, times by s0 pi, which is where that comes from. So that's, like I said, that's a useful identity to know, but like I said, it's on your equation sheet, so you can use that if you need to. Let's see. It's on the first page of the equation sheet. Another example. This you may see on past papers, because it's taken from past paper, but it's an example of a car on a road surface. Okay, vehicle of a mass of 1,000 kilograms. Suspension with a stiffness of 40 kilonewtons per meter and a damping coefficient of 2.3 kilonewton seconds per meter. Okay, is driven over a road which gives a vibrational input which can be characterized approximately by a constant spectral level of 0.1 g squared per hertz. Okay, so again, I've got this power spectral density, it's a constant, and I've been given the value in this case. Find the RMS, or root mean square, vibrational acceleration level of the car. So this system can be modelled as a mass with a base excitation. Okay, my input in this case is xb, okay, or x double dot b, and my output is going to be x, or x double dot. And between the two, I've got a spring and a damper. I've got the value for the spring, got the value for the damper, I've got the value for the mass. And so my equation of motion, okay, mx double dot plus cx minus x dot minus x dot b, okay, so you've got the relative velocity between the two, and here we've got a spring system, so it's the relative displacement between the two. You can rearrange it, putting all the x's on one side and the xb's on the other side to get that equation, and then to divide, or you can make the substitution in here, and then you get the output divided by the input will be your h term. And so there's the substitution in there. The exponentials will cancel out because they're the same on both sides. Okay, and I take my output, which is my x, divided by my input to give me this function, and that is the complex frequency response function. So the power spectral density of the car, the motion of the car, and like I said, we're talking about the acceleration, so it's x double dot. It's going to be my complex frequency response function, magnitude squared, times by the power spectral density of my input. Now, so obviously I can go through the process. My expected mean square value is going to be all of this lot. Okay. So here's my output. The integral of the output will give me this thing, but obviously the output equals this lot here. Okay. Which is just up here. So there's my input power spectral density. There's my complex frequency response function. And like I said, this term was a constant, so that can come outside, which is here. Okay. And you can solve it. But the thing is we were given this term in terms of frequency, in terms of hertz. So we have to do that conversion. Okay. Well, I said I've solved the integral first, but basically this is our identity. Okay. In this case, we've got these terms for A, B0, B1, A1, A2, and A0. So if I go back, we can take a look at that. We know that on the top, okay, we've got up here, we've got B0 plus J omega B1. So in this case, what is B0? Okay, and B1 is C, yeah? Look at this, B0, where is it? Okay, so B0 is times by nothing, and we've got J omega times by B1. So therefore, B0 must be K, and B1 must be C. And on the bottom, we've got A0, A1, and A2. So A0 is K, A1 is C, and A2 is M. And so you can replace those terms in this equation. Okay, so that's what we get. So we get K squared upon K, because B0 was K and A0 was K. So we get K squared upon K, so that's just K. A2 is M. B1 was C, so we get C squared over here divided by Cm. And so you end up getting M times K plus C squared upon Cm times by pi times by my power spectral density, my input. Now, like I said, I was given power spectral density, this term, in g squared per hertz. Okay, so that's my single-sided function in terms of frequency, in terms of frequency, which is in hertz. To get it in terms of omega, which is in radians per second, I have to multiply this by 4 pi. Okay. Sorry, no, that term is 4 pi times this. So I have to divide this by 4 pi. So it's 0.1 g squared divided by 4 pi, and then that will give me g squared per radians per second. So I take that term, my 0.1 divided by 4 pi, I stick it in here. There's my g squared. I don't lose that. Then I've got my the integral of that frequency response function. I now therefore have an equation for mean square, So I can plug in the values, I get 0.49 g squared, take the square root of 0.49, which gives me my RMS value, which is 0.7 g. Okay, so the root mean square, the measure of the magnitude of the varying quantity, okay, is 0.7 g.